In this study, we explore the task of leveraging auxiliary modalities which are only available at training to enhance multimodal representation learning through cross-modal KD. The widely adopted mutual information-based objective leads to a shortcut solution of the weak teacher. To prevent the teacher from losing information, we propose a novel cross-modal KD method called adversarial mutual information distillation, which maximizes MI between the teacher and the auxiliary modality model. Then, we maximally transfer information from the teacher to the student by optimizing the MI between them and minimizing the conditional entropy of the teacher giving the student. To implement the joint optimization, a novel training approach that contains the advantages of both constructive learning and adversarial learning is proposed. I'm Meng Xichen, a PhD student at Shanghai Jiao Tong University. I will introduce our team's work enhanced multimodal representation learning with cross-modal KD. Multimodal learning has shown much promise in a wide spectrum of applications. For many real-world applications, while one had to make predictions based on limited modalities due to inefficiency or cost concerns, it is usually possible to collect additional modalities at training, and our work focuses on enhancing multimodal representation learning by leveraging auxiliary modalities which are only available at training. Several attempts have explored to employ cross-modal KD to solve this problem, which use teacher models to guide the training of the student model with target modalities only. A typical practice is offline KD, which pre-trains the teacher model from full modalities and fixes it during the training. While such a setting enables the teacher to provide information-rich representation, it may not be favorable for the alignment of the teacher and the student, due to the large information gap between them. To better facilitate the knowledge transfer, online KD is proposed to jointly update the teacher and the student. One common solution is to maximize the mutual information between the teacher and the student. However, such an objective only focuses on maximizing the shared information, which is necessary but not sufficient to guarantee a complete knowledge transfer. As illustrated in Figure A, a shortcut solution is to simply make the teacher model capture less information, namely shrinking the entropy of the teacher. Under the framework of online KD, this paper proposed to simultaneously achieve narrowing down the information gap between the full modality teacher and the target modality student by maximizing IMS while minimizing HMS, maintaining the representation capacity of full modality teacher by maximizing IMA. For optimizing the 2MI, we introduce a constructive learning-based approach. For minimizing the conditional entropy, we introduce an adversarial learning-based approach. The objective of our proposed adversarial mutual information distillation is to minimize this equation, and the framework is as follows. Specifically, for optimizing the mutual information, we derive the lower bound on it by taking into account the correlation of samples within a class. Taking IMS as an example, we firstly design a latent variable C to indicate whether a tuple MS comes from the same class where C equals to 1 or not, where C equals to 0. Assuming that for a specific M in a mini-batch, there are KS from the same class and NS from the different classes. Then, the priors of C can be calculated by the two equations. Based on these two equations, we can derive the lower bound on IMS like this. Thus, minimizing IMS and IMI can be achieved by minimizing their lower bounds. To be specific, we minimize the two equations. This is a contrast learning-based optimization function. For minimizing the conditional entropy, we first derive its upper bound. After this, we minimize HMS by an adversarial learning-based approach. We introduce two additional discriminators, and update discriminators, the teacher and the student by a min-masking. We update the teacher and the student by minimizing this, and update discriminators by minimizing this, and the parameter lambda is adjusted adaptively. In addition to optimizing the 2MI and the conditional entropy, we also introduce the classification loss on both the teacher and the student, and the GASD loss between them for better alignment. Finally, the overall loss function is as follows. To validate the effectiveness of AMID, extensive experiments on 3 popular multimodal tasks, including video recognition, video retrieval, and emotion classification, are conducted. The experiments of these tasks are conducted on UCF51, ActivityNet, and IEMOCAP benchmark datasets, respectively. The results in the following 3 tables show that AMID outperforms a range of state-of-the-art approaches on all of the 3 tasks. In order to verify the effectiveness of our proposed method for capturing as much multimodal information as possible, the impact of using different loss configurations on UCF51 is studied in Table 4. Table 5 and Figure 5 evaluate the effect of each modification applied in AMID, and the sensitivity analysis studies are conducted for the hyperparameters alpha1, alpha2, and alpha3. We show the results in Table 6. The results show that the hyperparameters alpha1 and alpha2 are not sensitive within a certain range. Finally, the conclusion is as follows. That's all. Thanks for your watching.